Okay, so I know I said 5 after, but I don't think anyone else is going to come in. So let's go ahead and get started. Today we're going to talk about section 5.3. And it's really going to be all about integrating exponential functions and logarithmic functions. Or, I mean, not logarithmic functions, but 1 over x. So start off with, since the derivative of e to the x is equal to e to the x, when we undo the derivative, we should just get e to the x plus a constant, right? And that's all this simple exponential rule is telling us. And this general exponential rule, well, it's just an application of u substitution. So to see what some of this looks like, just so the folks at home know, this is slide 68. But just to see a couple applications of this, let's start off with this first example, 2 to the ex, or 2 times e to the x, I mean to say, dx. Well, in this example, we can pull out that 2, right? Multiple of a constant rule. So here we're just integrating e to the x, which we just said was e to the x plus a constant. The second example, we've got a little bit more work to do. Because we've got e to the 2x, that's like e to the u, right? So we need to stop and define u, which is going to be 2x. du dx then is going to be 2, and du is going to be 2 dx. So that means with u sub, we can rewrite all of this as e to the u du. Because we've got the 2, we've got the dx, and we're rewriting 2x as u. Well, this is just going to come out to be e to the u plus a constant. Substituting what u is back in, we're going to get e to the 2x plus a constant. And in this last example, we're just going to apply the sum and difference rule, right? So checking all of this out, comparing. Constant multiple rule, let's just pull out that 2. Integrating, we get 2 to the ex plus a constant. In the second example, we start by defining our u and our du dx. Applying u sub, and solving, we get e to the 2x plus a constant. And then finally, like I said, the third example was an application of the sum and difference rule. So why don't y'all take about 2 minutes to see if you can work this one out. So what do y'all think? What do we do here? Our u is pretty obvious, right? It's going to be 3x plus 1. So that means du dx is going to be 3. But we don't have a 3 in there, so what are we going to do about that? Exactly, multiply by 1. So we can rewrite this as the integral of e to the 3x plus 1 times 1 over 3 times 3 dx. So now we can pull that 1 over 3 out. Now we can apply u sub, right? Substituting everything in, we get 1 over 3, the integral of e to the u du, which is going to come out to be 1 over 3 e to the u plus a constant. So subbing everything back in, we get 1 over 3 e to the 3x plus 1 plus a constant. So really all we're doing here is rinse and repeating with these methods. Comparing really quick. Same thing, right? Identify your u, your du dx. You're going to figure out how to get a 3 in here. So if we multiply by 1, we can get that 3 in there and do the rest of the work from there. Okay. So in this example, it takes a little bit more massaging. This example, we've got 5x e to the negative x squared dx. So our u is going to be negative x squared, right? So our du dx, well, that's going to come out to be negative 2x. And our du is going to be negative 2x dx. So I'm going to do two things at once here. First, I'm going to pull out the 5, and then I'm going to multiply by 1 so that we get the negative 2 inside. Make sense? 5 times the integral of negative 1 over 2 times negative 2. The negatives are going to cancel, right? So we're just going to get 1 in there. X e raised to the negative x squared dx. Pulling out this negative 1/2 now, we we get negative 5 over 2 times the integral of e to the negative x squared negative 2x dx. And now we apply u sub. So this thing just integrates out to be negative 5 over 2 e to the u plus a constant. So when we substitute back in, now we're going to get negative 5 over 2 e to the negative x squared plus a constant. That's it. That's all she wrote. So setting u equal to negative x squared, we get du dx is negative 2x. You run through it just the same, right? Multiply by 1. Then we pull out our constants, rewrite everything using u sub, solve it, and then substitute back in our terms. Yeah? All right. So one of the previous classes, one of the previous lectures, I had said the power rule was for every case of n except where n is not equal to negative 1. So what I'm talking about is I had said in a previous class, this is the simple power rule. Right? And I said we could consider the example of x squared. When we take the derivative, we get 2x. When we take the derivative again, we get 2. When we take the derivative again, we get 0. When we take the derivative again, we get 0. And from this point on, we get 0, 0, 0, right? So the only way we can get a derivative to be 1 over x. So what I am saying is the only function that gives a derivative of this form is going to be the logarithm, right? So for that reason, the power rule doesn't apply to the case where n is equal to negative 1. Make sense? And also for that reason, the integral of 1 over x dx is equal to the logarithm, the absolute value of x, plus a constant. This makes sense, right? Because the natural log, it can only take positive values. We can't pass negative values through it, right? Excuse me. So we have to have that absolute value sign inside. Having said that, let's look at a couple examples. In this first example, we can use the multiple rule to pull out that polar. And now it's just going to come out to be 4 times the ln, the absolute value of x plus a constant, right? Now in this second case, we've got to be careful here. We can do the second case in a couple different ways, actually. We can apply u sub to the second case, or we can go ahead and simplify it. Either way will be legit. So I'm going to show the u sub method, but then I'm going to show the simplification. So here, we want to use u is equal to x squared, because we've got du dx up top, right? So du dx is equal to 2x. So du is going to be 2x dx. So now, by substitution, we got u, or my mistake, du over u, which is just going to integrate out to be the ln of the absolute value of u plus a constant. But subbing u back in, that's the ln of the absolute value of x squared plus a constant. Now, point on this. When we flip to the next slide, the book's not going to use the absolute value sign here. Why not? It's because x squared is always positive. And anytime you have something that's always positive, going through that ln after you integrate, that's when you can drop the absolute value signs. Otherwise, you have to have it. Make sense? So this other method would just be to say, all right, check it out. This thing reduces nicely. It turns into 2 over x dx, right? So integrating this, we get 2 times the ln of the absolute value of x plus a constant. Oh, wait a minute, these two things are not equal. They don't look the same, do they? What's going on here?
X squared.
Exactly. We have the power properties of logarithms, right? Log base whatever of x to a power can be rewritten as that power times log base b of x. So this thing, it happens to be equal to the ln, the absolute value of x squared plus a constant, which happens to be equal to the ln, the absolute value of x squared plus a constant. So both approaches got you to the same answer. So having said that, I'm going to jump to the next slide. Here, we just use that multiplying by a constant rule. Here, we're using u sub. But like I said, they're dropping the absolute value sign here, just because x squared is always positive. And in the last example, it's an application of u sub again. Okay, we've got time. So let's look at this really quick. We've got the log of 2x plus 1, or minus 1, I mean. Over 2x minus 1 dx. So here, u is pretty obvious, right? We're just going to use the denominator. So du dx is equal to 2, and du is equal to 2 dx. So by substitution, well, we can't apply it, can we? We can't apply substitution right away. We've got to multiply by 1 again, don't we? Totally almost forgot a step here. We've got to multiply by 1 first. To multiply by 1, since we want to get this 2, we're going to need to use 1/2 times 2. We can pull that 1/2 out. Get that this is all 1 over 2x minus 1 times 2 dx. Now, by substitution, we get 1/2 the integral of 1 over u du. But this thing is equal to 1/2 the ln, the absolute value of u plus a constant. So by substitution again, we get 1/2 the ln of 2x minus 1 plus a constant. Notice 2x minus 1, that thing can be negative, so we have to include the absolute value signs here. All right. So looking at the solution, comparing what we did to what the book did, same thing, right? Apply u, or find your u, apply the derivative to find du dx, multiply by 1, rewrite everything, apply u sub, solve, and then substitute back in. Yep. Okay, what about this example? How are we going to go about this? you all think? First, what's your u going to be? Yes. U here is going to be x squared plus 1. So du dx is going to be what? Exactly. So u is equal to x squared plus 1. The derivative of that is going to be 2x. So du dx, or du, is going to be 2x dx. So what now? Well, 6 is the product of 2 and 3, right? So why don't we bring that factor of 3 outside to get 3 times 2x over x squared plus 1 dx. That's a lot nicer, right? Because now we've got u sub here. Now we can say, all right, dope, applying u substitution. This comes out to be 3 times the integral du over u. This thing comes out to be 3 times the ln, the absolute value of u, plus a constant. Substituting back in. Get 3, the ln, the absolute value of x squared plus 1 plus a constant. And again, we can drop those absolute value signs because it's x squared plus 1. So comparing, setting u equal to x squared plus 1, du dx is 2x. Pointing out that factor of 3, rewriting it and applying u sub, we get the ln of the absolute value of u plus a constant. Substituting back in x squared plus 1, get our answer. So everything we just did, right? Okay. Some good examples here. They look vicious, they look horrible, they look awful. They're not as bad as they look, though. This first example, we're just going to apply the sum and difference rule here. I'm going to break up this fraction and apply the sum and difference rule after simplifying the integrand. So we have 3x squared plus 2x minus 1 all divided by x squared dx. This thing's going to come out to be 3x squared over x squared dx plus the integral of 2x over x squared dx minus the integral of 1 over x squared dx. This is going to come out to be 3 times 1 over, my mistake, just 3 times 1 dx, right? The other way we could write it is just as the integral of 3 dx. This is going to be 2 over x dx and this is going to stay the same. We could rewrite this as x to the negative second power. Power rule, right? Again, power rule, right? Because n is 0 in this case. Logarithm, right? So what we get then is 3x plus 2 times the ln of the absolute value of x minus 1 over negative 2 plus 1 times x to the negative 2 plus 1 plus a constant. Well, this simplifies. This is going to come out to be negative 1, right? So what we have in the end is 3x plus 2 times the ln, the absolute value of x, plus x to the negative first power plus a constant. So this first example, it looks horrendous. But after we apply the sum and difference rule, simplify it, turns out to be something nice, right? Now b here, b takes some playing with. What are we going to do here? It's not obvious right away. B, we have to use a trick. You got 1 over 1 plus e to the negative x dx. If you're looking at this and the first thing you say is, oh, I don't like that I have e to the negative x in my denominator, good. How are you going to get rid of it? Not quite substitution. You're going to use it eventually, but there's another trick in the meantime. What if we multiply by 1, but this time we chose 1 to be e to the x over e to the x? That's still 1, right? Good. So that times that what's going to happen now is that in the numerator, we're going to have e to the x. This e to the x times 1 is going to be e to the x. E to the x times e to the negative x is going to be 1. So this thing's going to come out to be e to the x plus 1 in your denominator, then e to the x in your numerator. Now let's apply u sub. Now, setting u equal to e to the x plus 1, or my mistake, e to the x minus 1, du dx is going to be e to the x. So du is going to be e to the x dx, right? So we can rewrite this now as du over u. We've got e to the x minus 1 in our denominator. We've got e to the x dx in our numerator, so u du. Integrating this, we get the ln of the absolute value of e to the x plus constant I should have written u, and then with substitution back in, this comes out to be e to the x plus c. That's all she wrote. Now for this last example, my mistake, I meant to write e to the x plus 1 in here. Plus 1. I apologize about that. For this last example, what you're going to want to do is apply long division and then rewrite your integral after having applied long division, then sum and difference rule, and then integrate. Make sense? So having said that, the very last slide has a bunch of example problems. I think there was one on here. No, it was in the homework that I wanted to use as a quick example for everyone. Yeah. All right. So in the homework, there was a problem. I'm not gonna lie to y'all, I kind of loved. It made you apply everything all together. Problem is something like this. How the hell are we going to solve that integral? Let's start by rewriting it, because that's ugly just to look at. So to rewrite it, this thing comes out to be the integral of 1 over x times the ln of x raised to the negative 5th power dx. After we rewrite it, it might become a little bit more clear here what we need to do. See, because now that we've rewritten it, I see something. If I rewrite this as u, I got du out here, right? Du dx. So let's let u equal the ln of x, and du dx is equal to 1 over x, and du is equal to 1 over x dx. So now, by u sub, we've got u to the negative 5th du. And what started off looking like an ugly, atrocious problem is now a lot easier to work with. So what's this going to come out to be? Negative 1 over 4, x to the negative 4th power plus c, right? I mean, u to the negative 4th power. So this thing, by an application of the power rule, turns out to be that. So substituting back in. Why don't you do the derivative of that really quick? If you were to undo that integral and take the derivative, you get back to that form over there, don't you? So the moral of the story here is that some of these u subs may not be obvious right away, and this is one of the reasons why we like to rewrite everything in terms of powers, right? Because it makes it a little bit easier to compare and contrast what's on the paper. And we've already seen a couple examples where we've had x raised to a power in the denominator and are like, well, this isn't the power rule, you know? So I would always suggest going back, rewriting everything using powers. That way you can kind of see some relations about that. The more ways you can rewrite things, the more you're going to see anyhow. Saying that, was there an example on here that I wanted to show y'all? Not on here, but there was something I wanted to make a point of in the notes. I don't remember if I made this point. If I can find it. Point about u sub that I wanted to show y'all. Wasn't it? Was this these two problems? Okay. So these two problems, for the folks at home, what I am looking at is slide 47 and 48, I think. Double check. 48 and 49. So what we've got looking at these two problems are two problems that look very, very, very similar. The difference being what's outside our parentheses here, right? We've got a -8 and an x here. And the point of all of this is just that looking at a problem, it's actually very much the same point I was making here. Looking at a problem, just because two things look very similar does not mean you're going to apply the exact same method to them. Sometimes what you're going to end up having is one problem is solved one way much more easily than it is the other way. Makes sense what I mean? So in the case of this first problem, you would use u sub. In the case of the second problem, you would be best expanding it out and then solving it. Having said that, I'm going to let y'all go unless you have questions about the homework or anything else. Excuse me. So y'all are free to go. Stick around if you have questions. Also, there are 8 questions on the exam. 8 questions, you have 90 minutes. It is due Monday night at midnight, I believe.